All right, now that we have the definition of the definite integral, I want to go through a few examples of actually using that definition to evaluate integrals. In some sense, this is going to look a little bit like the reverse of what we did in the last two examples. So to start with, I'm going to say use the definition of the definite integral to evaluate the integral from 3 to 8 of the constant function 2. And I want to emphasize the fact that we're prompted to use the definition. So as we go on in this course, we're going to have other ways of evaluating integrals. And primarily, we'll think of the other ways as being shortcuts in comparison to this. So if ever the question prompts you to specifically use the definition, then we do need to approach it in the way we're going to see here. So now what you can think about is here, we need to, like I said, reverse what we did in the last several examples. We need to express the given integral as a limit as n approaches infinity of the sum from k equals 1 to n of f of xk delta x. Once again, I'm making an arbitrary choice of setting it up as a right-hand sum and not putting in that xk star notation. So just like I did before when going in the reverse direction, I'm going to start with delta x. We can find delta x here as the length of our interval divided by our number of rectangles n. And so delta x is 5 over n. X sub k, remember, is a plus k delta x. A is 3, the leftmost point of my interval, and we know that delta x is 5 over n, so this becomes 5k over n. Our function f of x, in this instance, is the constant function 2. So normally, as you see in our sum up here, I need to specifically evaluate my function at the xk I found above. So I would plug in 3 plus 5k over n. But for this function, no matter what you plug in, the output is 2. So it turns out it doesn't really matter what I found xk to be. I get 2. This next example I do, we'll see how that dependence on xk does arise when I have a non-constant function. So at this point, I'm ready to put in what I've found. So the integral that we started with is equal to the limit as n approaches infinity of the sum from k equals 1 to n, where what I'm going to do is now substitute in the pieces I've found. My f of xk is 2, and my delta x is 5 over n. So what I need to do is evaluate the limit of this sum. And I'm just going to simplify this to 10 over n. So I think it's helpful to notice that the way I want to approach this is kind of from the inside out. So the last thing I want to do is take the limit. I want to first work on this summation. And I'll point out that we can then notice that the sum here is constant with respect to index k. So as I'm changing k from 1 to 2, etc., all the way up to n, I'm not changing the terms. It's simply 10 over n. So I can think of the sum as 10 over n plus 10 over n and so on, and even my last term would be 10 over n. So the question is, how many replications of 10 over n are there? How many times am I adding that constant to itself? The answer is n times, because my sum is from 1 to n, so I know that there are n terms. So if you add a number to itself n times, that's the same thing as multiplying that number, in this case 10 over n, by n. So if I took the number 2 and I added it to itself 5 times, 2 plus 2 plus 2 plus 2 plus 2. That's the same thing as 2 times 5. So that's exactly what I'm saying here. What's nice about that is the n in the denominator cancels with the n in the numerator. This becomes the limit as n approaches infinity of the constant 10, and the limit of any constant is 10. So I have now used the definition in order to evaluate this integral. So if the function is slightly more complicated, so not a constant function, let's look at a linear function. Again, use the definition. Whoops. The definition of the definite integral. To evaluate the integral is due from 1 to 4 of 2 minus x. And notice one thing here is I have to give you a sum. So given that the sum from 1 to n of k is equal to n times n plus 1 over 2. In this course, we're not going to go through the derivation of that, so that is not something you're expected to, first of all, know why that's true, but second of all, you're not expected to commit that to memory. If ever we ask you another question where that sum is required, just like I'm doing here, I could just give it to you in the problem. So that's given information. And it's also not supposed to be clear why we need that yet, but as we work through this problem, that will be needed. So my approach is going to be very similar to what I did up top. And the first thing I want to do is start with delta x. So I'm going to need another page. So let's let's find delta x. So I know the length of my interval here, 4 minus 1, is 3. So delta x is 3 over n. I can find xk. That's going to be our leftmost point in the interval 1 plus k delta x. So 1 plus 3k over n. And unlike our last example, our function is not constant. Here, f of x is defined to be 2 minus x. So f of x k is f of 1 plus 3k over n. That means we take 2 and we subtract the input 1 plus 3k over n. And I want to simplify that. That's going to be 1 minus 3k over n. So at this point, we're ready to substitute everything in. I could say here that the desired integral from 1 to 4 of 2 minus x by definition equals the limit as n approaches infinity of the sum from k equals 1 to n of f of xk, we just found that to be 1 minus 3k over n, times delta x, which we computed to be 3 over n. So we get a more complicated looking sum, and in particular, one thing that's significant is there is a k inside of our summation. So like before, my goal is to simplify what's in the brackets here before taking the limit. And one thing I can do is distribute the 3 over n. So this becomes 3 over n minus 9k over n squared. And from our properties of sigma notation in the previous lecture, I can break this up into the sum of 3 over n minus the sum of 9k over n squared. So I want to come back to the given information and remind you that we were given a formula. We were given this. So I should expect to use that at some point, and I'll point out that it's the sum of k, and I can identify that's kind of hidden in here. So another thing we talked about with our summations is that you can factor constants with respect to the index outside of the sum. So in this one, the index is k. So what I've circled in blue, that has to stay inside of the sum. But 9 over n squared is constant with respect to k. So I can bring that as a multiplier outside of the summation. Importantly, I cannot take it outside of the limit because the limit is dependent on n. So all of those things must stay inside of the limit expression. But now, this thing here is exactly the given formula in the beginning of the problem. So I can replace that with n times n plus 1 over 2 when I'm trying to evaluate this limit. This first sum here is very similar to what we ended up with in the last example. We saw that we would add 3 over n to itself n times. Consequently, that's equivalent to 3 over n times n. And again, just to reiterate, I'm replacing the circled blue summation with what we were given it to be equal to in the problem. So notice that now this just becomes a limit problem. So if I try to simplify this, I have these cancel. And the other thing to think about is this second limit here is essentially a quadratic in n divided by a quadratic in n. So we could use L'Hopital's rule, but the other thing that can be helpful is if you have a polynomial divided by a polynomial and you're sending n to infinity, you want to look at the degree of the top and bottom. So the top is degree 2, the bottom is degree 2. So in that instance, when finding the limit, so this first one is just the constant, what we can do is simply take the ratio of the leading coefficients. So we're going to have a 9n squared in the top and a 2n squared in the bottom. And, sorry, this should be not plus, but minus. Consequently, the limit of that second expression is going to be 9/2. And so we put this together and we get our answer. Okay, so now we've seen how to apply the definition to evaluate definite integrals directly, and in particular we've gone through a constant function and a linear function. These functions will make a reappearance in our next video when we'll see another way we can go about evaluating those definite integrals.